Hello, this is another tutorial, and this is a tutorial that should cover the analysis pipeline of high-resolution layer-dependent VASO data. So on the blog, layer-fMRI.com, we already discussed many different substeps of the analysis and which details are important. Today, I don't want to focus so much on the details, but instead I want to give a good overview of the entire arc of the analysis pipeline. So starting from raw EPI data up to the final layer-dependent fMRI profiles that we end up with. In this analysis pipeline, I want to use a few software suites that are out there already, including SPM, AFNI, my own software package, Laney, and GNUplot, just for some 1D plots there. You don't really need GNUplot, you can plot with anything. You actually also don't really need SPM in case you have strong opinions about its dependency of MATLAB. You can use AFNI instead. However, those AFNI alternatives are not really that well optimized for high resolution data from my side just yet. You can download the data at this link, which is Google/4KMEFC. And when you go there, then it directs you to Google Drive, and then you can download the entire thing by clicking this link. This will be a zip file, and it might take a tiny little bit to download. So I'll download it already. It's about 150 megabytes big. You can unzip this zip file, and there you have all the example data that I want to go through today. Let's dump them here. So here you have 4 folders. Most of the data, or the only file that we are actually mostly looking at today, is in EPI_raw, and this contains 2 time series. One, the signal mean, which is just the mean time series of the BOLD VASO data as they come from the scanner, and also a phase. We will not look at the phase a lot. It's just here for reference. Also, just for reference, I included a few anatomical, even higher resolution data. For example, an MP2 range dataset of the slab covering the motor cortex, which is also covered from the EPI data, the corresponding T1 map, phase in case you want to identify veins, or also a whole brain average of the same person being scanned at 0.7 millimeter resolutions, I think 10 times, and average together. There are other folders with all the scripts that I want to go through today. For example, in EPI_analysis, there will be a script for the motion correction, for the BOLD correction, and then later for the activation estimation. And later in the tutorial, I will also go through the individual layering. So maybe a few words about the data. These data were collected at NIH in a study from 2016-2017. Maybe we can look at them to give you a better view. This is 0.7 millimeter, or actually 0.745 millimeters, and slightly thicker slices of 0.25 millimeters. This is a 12-minute data set with a repetition time of 1.5 seconds. Since this image is acquired with a VASO preparation, you have actually every 3 seconds a repetition of the entire contrast, meaning that we start with a BOLD image, then we have VASO, BOLD, VASO, BOLD, VASO. So only every 3 seconds you have a pair of both images with blood nulling and without blood nulling. So while the actual repetition time is 1.5 seconds, you end up with a temporal resolution of 3 seconds. And already surfing through here, you can see that every other TR has a big signal, and then we have a low signal, big signal, low signal, and you can see some modulation here. This modulation in the motor cortex, which would be right over here, is coming from a finger tapping task. And this finger tapping task consists of 30 seconds of rest, not doing anything, versus 30 seconds of tapping your finger like this. And the whole thing 12 times, so we end up with a 12-minute data set. And I think those are the most important features of this data set. Maybe it's important to say also that this was acquired at 7 Tesla with a 32-channel Nova coil. The first thing that we need to do is the motion correction. And at these very high resolution data, like this one here, we are always suffering from the fact that we need to use very low bandwidth. So we have problems that the brain is not really moving as a rigid body, but there are these nonlinear effects such as like time varying distortions. So it makes sense to do the motion correction based on a specific ROI only. For example, only based on the motor cortex that we care about here. So for that, we need a manually selected area, like a mask, and let's draw this. You can do this in fossils, for example, by pressing the Option key and E key, going in edit mode here, and you get all these additional buttons. For example, this button that makes a new empty data set with the same dimensions as the previous one. And when you select the pencil, let's make it 3D and a bit bigger, then we can nicely draw little regions of interest that cover the motor cortex right over here. Maybe we go up a bit, make it nice and big, but not too big to include all the side areas that might have different motion and therefore screw up our motion estimation. So let's save this data set with this save symbol here. Maybe let's put it in another data folder, the analysis folder, and let's save it as moma.nifty, which stands for motion mask. Let's save this, and let's also make a copy of the magnitude here, put it in the same folder. So now in this folder, we have the time series and the motion mask, and we also have this moco.sh, which basically runs the motion correction. And you can see the content here, it's very tiny. So basically what this script does is it kind of overrides the first 4 time steps, because there we are not really in steady state just yet. It makes a copy of it as basis A and basis B, and it also writes down the number of TRs, dumps it into a file, because that's then used from SPM script in MATLAB. And so this line basically calls MATLAB. Note that this line might be different for your machine. This just calls MATLAB with the script called moco batch. And the content of this moco batch is stuff from SPM, where you're basically just sorting the odd and the even time steps, because we have BOLD and VASO acquired interleaved, and because they have very different contrast, they kind of look different. And sometimes when you try to register a different T1 of the VASO to the BOLD, it can look very, very bad. So it makes sense to do the motion correction on each contrast separately, on the BOLD and on the VASO. So here it basically just generates an array that tells SPM later which dataset is a BOLD and which is a VASO. And here you have all the SPM motion correction parameters that you might care about and might modify. For example, this is saying that we want to have local weights. For example, in this MoMA file that we just manually generated, it tells you which kind of interpolation you're using. I would really advise to use at least linear and higher. I use a spline 4th order, and you can also choose if you want to register to the first or the mean or so. So let's see what happens when we run this. Now we are already in EPI analysis, this folder. So now let's run the moco. And you can see that it calls AFNI in this file to override the first 4 TRs. It already dumped the number of TRs into this file called NT, and we see that we have 483 TRs in our file. And you can see that it already started MATLAB and did the alignment. So it's done with the BOLD part already, and it's not done with the VASO part yet. This will be coming up in a few seconds. So it did the estimation, and now it needs to write the files in without these estimated motion. And we are almost done. In a second. So this is particularly fast here because the motion mask does not really cover so many voxels. When you have bigger data sets, this can take much longer. And now we are done with the motion estimation and correction. So we can look at the motion traces. This is done in GNU plot, and you can basically see a few features here. You can see that we have motion traces in all three directions. This is the displacement in millimeter. You see that this subject did not move too much. However, it's also not super beautiful. So especially in the phase encoding direction here, the blue and the turquoise lines have motions that are in the range of the voxel size. So this is already the limit. If there's a lot more motion, then you might need to consider throwing this data out. We see that the motion is biggest in the phase encoding direction, which is also due to the fact that we have these very low bandwidths. So this might not be real head motion, this might just be field motion. What's important to note here too is that for BOLD and VASO, the null and the not null time series, we have very similar motion estimates. If those are not similar, then you need to do something about it. For example, trying to modify the script earlier, for example, changing the fact if you're registering to the first or the mean, or also modifying the motion mask. So this looks all right for now. So let's see what this gave us. This gave us now two data set, the null underscore basis B and the not null underscore basis A. So if we load them into fossils, then you can see that the null one is actually empty and in the first image. Maybe it's better visible when we look at the time series too. So you can see here that when we zoom in, these images are interleaved acquired. So you have a nulled, then zero, not nulled, then zero on either case. So it has a lot of zeros in there, but taken together, they are the motion corrected time series of the odd, even, bold, VASO time series. Now that we did the motion correction, the next thing we need to do for VASO is the bold correction. Because VASO is also acquired with EPI, it always has some unwanted bold contamination in there, as explained in the blog. And we can easily correct that by just dividing the blot nulled image with the not nulled image. And this is all done in the file right here, where we can go through it real quick. So the first lines are basically removing all these zeros that I just told you about. And so we have one nice, clean, connected null time series and one bold time series. This is also upsampled, and because BOLD and VASO are acquired interleaved, it means that the time when we acquire the VASO, we actually don't have a BOLD. So we are temporarily upsampling the BOLD to estimate what the BOLD contamination would have been if we would have acquired them not interleaved, but at the same time. This is done here. And the BOLD correction then is actually happening in this layer-fMRI a command right here. And because we did this upsampling, we also need to take care of the header, meaning that we are now actually working in the real TR space of 1.5 seconds, not for each, not 3 seconds. So let's run this real quick. And then we can see what it gives us. So you can already see that we have a nice clean BOLD time series without all these zeros, and we already have this VASO time series here. So maybe let's look at them real quick in FSL view. So right here, maybe we go out of the edit mode here. You can see that we don't have any time series. So here we have time series now of BOLD and VASO, and now you see that it's noisy and stuff, but we don't have all these zeros anymore. So at this location that we selected right here, you can see maybe that it's going up and down for BOLD now, and in VASO it's also kind of going up and down. If we go through a few voxels, especially maybe if we go through a big vein, there you might see it clearer in BOLD that we have a task going on. So the BOLD and BOLD correction and the separation of BOLD and VASO time series seem to work. This is what happened here. What this also spits out is trial averages. For example, BOLD trial and VASO trial averages. And we can look at those time series too. So, excuse me. So here you basically see temporal averages. So this is now for all the 12 trials. They are averaged together, and you can see that for BOLD, we start with baseline, and the task starts at about TR of 20. So BOLD is low during rest and then increases during activity. The opposite is true for VASO. It's up during rest and then decreases during activity as expected. The next thing that I always try to do is also do some anatomical reference acquisition estimation directly in EPI space. So VASO, it looks kind of very similar in the sequence domain as a conventional MP2 range anatomical sequence, with the advantage that it's directly acquired in EPI space from the same data that I used for functional space. So for example, by looking at the T1 weighting in EPI, it gives us a nice and clean T1 contrast where we can kind of already see the borderline between CSF and gray matter and white matter. This is basically done with this line by looking at the temporal variance of the BOLD and not BOLD images. Another thing that I found very important is always to look at some basic measures of quality assessment, especially when you work with these non-conventional data sets for high resolution or VASO. And maybe the most important things are looking at the mean, the standard deviation. I also found it helpful to look at the skew and kurtosis. So maybe let's look at those. So here we have the skew of VASO and maybe also the kurtosis, if I find it here. So you can see that these are mostly flat, which is a good sign. This basically tells you something about the distribution of noise. So if it's very non-Gaussian noise, then you get higher values. This is particularly visible when you have severe ghosting or when you have like Riccian noise, like in the back here. In the brain, it looks like completely uncorrelated. Maybe there's something going on due to the activity. But aside of that, it looks all right. And maybe let's also look at the TSNR, just to give an idea how big it is and how much to expect from these kind of data. So VASO TSNR, and for comparison, BOLD TSNR. So you can see that this would be the BOLD, which is really super dominated from big veins. So in the vein here, BOLD might have a TSNR of 8.6, whereas VASO has 8.53. In gray matter, you can see that BOLD has about a TSNR of 36, and VASO is much lower in the range of 23, which is, I think, all right. Usually my rule of thumb is that you should be definitely bigger than 15. If it's bigger than 20 for VASO, it's also advantageous, but sometimes we cannot do. So this is all right. And this comes also from the fact that we use thicker slices, not isotropic submillimeter voxels. And in motor cortex, this is easily doable to use these thicker slices because you can align the slice perpendicular to the cortex. So you still have layer-dependent specificity, BOLD correction, and also some basic quality assurance. We can go ahead and do the first activation analysis. And this can be done in two ways, and both of them are collected in this script activation.sh. So here I'm showing you two ways. The first way is very, very simple. It's just averaging the time courses during an activation period and rest period and calculating the difference between those. So here I know that in my 30 MTR time interval, the TRs between 9 and 19 are approximately a steady state rest, and between 29 and 39 is approximately a steady state of activity. So I'm just doing a subtraction of those and normalizing them to baseline. Also important to note here is that VASO is a negative contrast, so I'm not really subtracting activity minus rest, but rest minus activity to have a positive activation measure at the end. You can also do this in a GLM. For example, here I'm using the 3D deconvolve from AFNI. However, as soon as you use this GLMs, you need to assume a certain canonical HRF, and that might actually be different across layers. So it's always harder to interpret those data because you never really know if the deeper or upper layers are stronger than the upper or deeper layers because they have different HRFs or because they have a different neural activity. So I'm extracting both of those measures and doing the same for BOLD again. So maybe let's just run this real quick and then see what comes out of it. This was AFNI and the same for BOLD and VASO. And now we have all these stats and we have the delta BOLD and delta VASO. So maybe let's look at the delta VASO here. This is now subtraction. So this is not inversely weighted with noise. So we have all these false positives outside the brain because there we are basically dividing by 0. So maybe we can look at a decent window here. So this is divided by baseline, so it's 100% would be 1. So let's look at the range between maybe 3% and I don't know 6 or 7%. Let's make it colorful. We actually don't need the time courses anymore, and this only makes it look weird. So here we have the activity right on the EPI and anatomy, and you can see that on the sensory cortex, this would be the index finger probably. There we have activity. On the motor side, we have this kind of activity right over there, and you might be able to see that we have activity in the upper layers right here, and also another big bump of activity in the deeper layers. Maybe let's look at another slice right here. So again, we have activity in the sensory cortex and in the motor cortex. Maybe you are able to identify two stripes of activity, an upper one over here and a deeper one right over here. And maybe let's compare this with the BOLD. Again, BOLD is usually stronger, so activity changes in the range of 5% to maybe 12%. 5 was actually maybe too conservative. Let's make it also 3 and colorful. So you can see in BOLD, at this resolution, we're actually high enough that we can separate sensory from motor cortex. Maybe not so much right over here. There we have some leakage going on of motor cortex to sensory cortex. If it's true, it could also be that sensory cortex is also activated. Hard to tell in BOLD. And also in the deeper slice here, it's basically one big blob, whereas VASO can maybe better separate the upper from the deeper peaks right over there. Also maybe here in this would be a axial-like view, you can see these double stripe patterns right there. So those are the features that we're interested in and also want to look at in the layer domain later. So let's do that. So in this last part of the tutorial, where I'm in a new office now, I want to look at the activation estimates that we just calculated in layer space. And let's do this layer analysis in a new folder, in this layer folder, because this one is already quite busy. So let's copy paste the data sets that we want to look at it. For example, the delta BOLD and delta VASO and a T1 weighted as a reference, and copy them into the layer folder. Now in this folder, we want to execute all the commands that are written down in this layering.sh file. So let's open that, and also let's open a terminal in that folder. Put it down there. The first part that we want to do to get towards the layer space is to upsample our data, namely by a factor of 5. And this upsampling is necessary because we want to define the borderlines of gray matter and white matter on a finer grid than the actual effective resolution of 0.75. And this allows us to have smooth surfaces and not kind of stepwise borderlines between gray and white matter. This is executed then on the T1, on the BOLD, and the VASO. So let's execute this command by copy pasting it into the terminal, and this gives us 3 additional files: scaled VASO, scaled BOLD, and T1. So this is just a spatial upsampling. The upsampling in this case is only done in the within slice domain. So you can see that in slices, we have now upsampled resolution of about 150 micron, whereas the slice thickness is still the same, because we're still assuming that we are perpendicular to the cortex. So this would be the hand knob over here. We have a double kind of epsilon-like shape in this participant, and this is actually pretty deep down in the central sulcus already. So the double hand and the double stripe pattern is mostly visible in the evolutionary older part of M1, the upper one, which might be somewhere here or here. So if we can zoom in there, so I would guess that the hand activation would be somewhere here. In order to estimate the layers in this area, the next step requires the knowledge of borderlines of gray matter and white matter. And this can be estimated with free surfer or clustering algorithms, whatever you like. So here, let's just do a quick and dirty method and just draw them manually. You can again do this in fossils by pressing the Option key together with E, which would be, I think, the Alt in Windows. And then you have this Edit Mode buttons. And for example, this button here that generates a new empty data set, and the pencil button because we want to draw in this data set. Let's get a consistent regime here. Let's draw in green. And let's start with a small pencil sizes. So here we can now, for example, draw with 1 the borderline between gray matter and CSF. So I'm somewhat roughly drawing here in the middle of CSF, following the cortical ribbon. Maybe that's already enough. Then I choose a fill value of 2 to get the borderline between gray matter and white matter, which might be somewhere here. And for now, it doesn't really matter if it's super accurate, because now we want to compare BOLD and VASO. And as long as we are looking at all the data in the same domain, slight shifts towards white matter or towards gray matter doesn't really matter, or shouldn't really matter. So we close them with a fill value of 3, and we can fill the entire thing with the fill tool here. We fill continuously with connected voxels. We click in there so it fills it, and we fill it, then execute that with this button. We can save this as a RIM file, for example, rim.nifty, and execute this command. So this estimates now 11 different layers in a vicinity of 40. The 40 is not so important. You probably don't need to worry about that too much. So let's see what kind of layers we got here. So these would be the layer estimates. Let's make them a bit colorful so we can better appreciate what they're showing us. So here we have now 11 different layers that follow the cortical ribbon based on these borderlines that we just estimated. Actually, I probably am only interested in this middle part here, where we are interested in the finger representation. We don't just want to like average the entire motor cortex. Actually, only this part of the Brodmann area for A, the evolutionary older part. So let's constrain it a bit. I just went back here a few times in the drawing steps, and let's draw smaller borderlines. For example, somewhere between here, we are only interested in this part of the motor cortex. And let's fill it again with the fill tool with value 3, and execute that and save it again, override. So we do the grow layering again, and let's actually also estimate the cortical layers within that masks. So now you can see that we did the layering with the new RIM file. We also use the layers that we calculated to extract the average activity within those layers. And for that, I'm just averaging the activity within the different layers with the AFNI command 3D ROI stats. And I'm averaging the signal. I'm looking how variable it is and how many voxels I have. And then I'm plotting this just as a 1D plot. So this is what we see here. The top line is basically just the number of voxels within that layer. We have this outlier top and bottom because here we have more voxels. The middle line here refers to the variability within that mask, and you can see that the variability is rather constant, maybe here a bit higher, and towards the upper layers the variability really increases, so we can trust the upper layers less, and this is mostly due to the fact that there we have more physiological noise. Down here is the most interesting part. This is the VASO signal change averaged within the different cortical layers, and you might be able to see a double peak response here. We have a huge activity in the deeper layers, it goes down, and then we have this kind of shoulder or secondary peak in the upper layers here, which I would like to interpret as input up here and output down here. When we close this, it continues and does the same thing for BOLD. So for BOLD, it looks slightly different in the sense that we have much more variability in the upper layers. So the big veins in the upper layers result in much more physiological noise up there. This means that the entire top half of the cortex is more suffering from these physiological noises compared to the deeper ones. So you always have more noise, in this case, in the upper layers compared to the deeper ones. So be sure that when you interpret activity measures, don't really rely on statistical set scores, because they might be higher in the deeper layers simply because the noise is lower there. Importantly, the signal change of BOLD is basically this gradient. The CSF borderline would be in the upper layers here, and then the signal decreases going down the cortical depth. And maybe you might be able to see that it's not a completely straight line. There might be a peak up there and then some sort of a shoulder down here, but it's very hard to see that. It's mostly just this big gradient. And in the last step, I'm also running a GNU plot script that compares the BOLD and the VASO at the same time, which does not seem to be executed because I have a typo. Excuse me. So now it should have also plotted the BOLD and the VASO profile. So you see that for the VASO in blue, we have a reduced activity in the upper layers compared to BOLD. And there's actually another typo here, and I apologize for that, that the bottom line should be VASO. So let's execute it again and open it up again. And now we have proper descriptions. So the activity is on the left and the cortical depth is the x-axis, and on the right hand side we have CSF. So CSF in BOLD is very strong, and then it decreases with cortical depth, whereas VASO might be able to depict this double peak response. And that's basically it. It also saves the layers and layer activities as text files here in a kind of ASCII format as the different columns that you can do further analysis with that. For example, then look at the same area and the activity across the layers for different tasks and how the upper and deeper layers are differently modulated. If you have questions, leave them in the comment section or at the blog, and I thank you very much for